Give me a second here. Continue. All right, so we're going to scoot ahead here. How did things go yesterday? Good. All right. Like I said, I planned on being gone. I knew I was going to be gone. I had a doctor's appointment. So hopefully those videos helped. We're going to review how to solve rational equations, and then we're going to spend a lot of time talking about rational inequalities. But we're going to move ahead here a little ways. We're going to look at some applications, I think is what we want to do, because that'll help not only solve these, but that will also help us come up with how to solve these word problems. So I should have been moved ahead here. Okay, this is where I want to be. All right. So basically, the way we solve rational equations is we get rid of fractions by the LCD method, right? We multiply both sides by an LCD, a least common denominator. We eliminate the fractions, which could turn out to be a linear equation, could turn out to be a quadratic, could turn out to be whatever. Okay. All right. Now, this is an example where we're going to set up a system of equations. Excuse me, not a system of equations. Back up there. We're going to set up a rational equation that we're going to solve here. All right. We're going to set up a rational equation that we're going to solve here. All right. Then we'll review the process of solving those. And if you have other questions, we can cover those. This is on a river. A kayaker travels 2 miles upstream and 2 miles downstream in a total of 5 hours. In still water, if the water wasn't, if there was no current, the kayaker could travel at an average speed of 2 miles per hour. Based on this information, what is the average speed of the current of this river round to the nearest tenth? Okay. So this is a word problem where we're going to end up with a rational equation. Okay. All right. So what do we know here? We're going to use, realistically, let me get this set up here. We're going to use distance equals rate times time. Okay. We're going to go upstream and we're going to go downstream. Now, if we go upstream, we're going to go against the current, correct? If you go upstream, you go against the current. If you go downstream, you go with the current. Okay. So if I go upstream, I go 2 miles, and that's going to be my speed I can kayak minus the speed of the current. And that's going to be a time, I'm going to call that T for time. Okay. Any questions on that? 2 miles, the current is how fast I can kayak minus the current. And then my time would be T. All right. Questions there? Now, if I go downstream, it's still 2 miles because I got to end up back home, right? But what's true about my rate? The current is going to help me. Okay. And that time isn't going to be the same. So I'm going to call it H. Because obviously, if the current's helping me, it's going to take less time, correct? So those times aren't going to be the same. All right. Those times will not be the same. All right. Now, what do we know about this situation? The whole trip took how long? 5 hours. That should mean that T plus H, shouldn't that equal 5? Is that correct? So the time for the upstream leg plus the time for the downstream leg should equal 5. All right. That's where we're going to end up with a rational equation. Well, if I solve this equation right here for T, I believe T is 2 over 2 minus C, isn't it? Any question to that? And if I solve this equation for H, I'm going to get 2 over 2 plus C. And then that should equal 5. So that's that equation we're going to have to solve here. I'm going to write that down because I'm not sure if the next slide has the work to solve it or not. I think it does, but I don't want to lose it. Okay, but that's how we can set up that equation. We use distance equals rate times time, and I think we used that last week too, didn't we? A little bit. But basically the times had to add up to 5. So that's a rational equation, like you maybe watch those Khan Academy videos. That's what show you how to solve them. Okay, any questions so far? All right, well, this isn't working very well. Under there in the black print there, you can see 5 equals 2 over 2 minus c plus 2 over 2 plus c. That's really that equation we have right here, correct? Now, they're saying that the LCD is 2 minus c times 2 plus c. Do you all agree with that? Sometimes to find an LCD, do you multiply the denominators? That's what we did here. Okay, so we have to take both sides times 2 plus c times 2 minus c. Well, that's going to allow us to do a little canceling here. And it's going to allow us to do a little canceling right here. Because that was the whole goal here, was to get rid of the fractions, right? To get rid of the denominators so that we don't have to, deal with them. Okay. Question so far? Well, then we end up with that. Okay, so now we're going to have to rely on what we learned back in chapter 2. I think we're going to have to do a little distributing here, distributing there, and are we going to have to do a little FOIL work here? Multiply things out. All right, so here we go. All right, if you multiply here, you're going to get 4 minus c squared. And then we have that times 5. That's how they came up with 20 minus 5c squared. All right, this comes from there. And this comes from multiplying that out. All right. Any questions there? All right, so we had to do a little FOIL work. 2 plus c times 2 minus c makes a difference of squares. 4 minus c squared. Okay. Well, now we got to keep on our algebra path here. What happens with 2c and negative 2c? How many c do they become? What's 2c plus negative 2c? 0c, yeah. So we end up with that, which we should be able to solve. Okay, they ended up subtracting 20 from both sides. You got negative 5c squared equals negative 12. And basically that would mean c squared equals 12 over 5. How did they get 1.5? Square root. Square root of 12 fifths is approximately 1.5. Now, does that seem like a reasonable answer in this problem? Could the current be 1.5 miles per hour? Considering that the kayaker goes 2 miles per hour, I think that makes sense. I think that would work, okay? And we wouldn't include the negative answer because you couldn't have a negative time. Or this isn't time, excuse me, this is the current, I should say. But you wouldn't have a negative current. Okay. All right, so that's why we use that LCD method, so that we can do this, this crossing off. And that eliminates fractions, which allows us to rely on either quadratic algebra or linear algebra to solve. Okay, so hopefully you got that out of the lesson yesterday. Word problem's a little more difficult because we have to set up the problem. Okay, we had to come up with the equation. It wasn't just given to us. Okay, but once again, we use distance equals rate times time. All right, now that's just kind of trying to get us back into the swing of things with section 5. From what you were assigned for today, do you have any questions over any of those? You did 1 through 10 and 19 through 27. Do you have any questions on any of those that you would like to go over? Okay, because then we're going to move on and talk about some other things here, but I want to give you a chance to go over anything that you feel you need to. Is this solving this equation more complicated than what you did yesterday? I think so. Okay, I think so. All right, there's a little bit more to this. Okay, but we'll move on. All right. Speed of the current's about 1.5 miles per hour. All right, here's another application. Now, this is a work application. Now, instead of distance, we're going to say work equals rate times time. All right. It says Natalie can finish a 500-piece puzzle in about 8 hours. When Natalie and Renzo work together, they can finish the 500-piece puzzle in about 4.5 hours. How long will it take Renzo to finish a 500-piece puzzle by himself? Same thing. Are we dealing with time once again? The time that Renzo can do the puzzle plus the time that Natalie can do the puzzle. Okay, we're going to work together here. So we're dealing with time. Distance equals rate times time is a lot like work equals rate times time. All right, very similar. Natalie's rate is 1/8 of the puzzle per hour. One puzzle in 8 hours. That's where we get 1/8. Okay, that's her rate of work. Renzo, we don't know how long it takes him to do the puzzle, so we'll say 1 equals R times H. That's where this comes from. Okay? We don't know how fast he can do the puzzle. That's what we're looking for. All right? But what we do know is that if they work together, they can do it in 4.5 hours. Okay? But what we do know is if they work together, they can do it at 4.5 hours. All right? So now we're going to put those two, rates together, and we're going to go from there. I'm going to stop here and see if you have any questions. Work equals rate times time is a lot like distance equals rate times time. Okay, it's just work rather than distance. All right, now we get that equation. This is how much work Natalie does in 4.5 hours towards the puzzle, right? This is how much work Renzo does in 4.5 hours. And we know that in 4.5 hours, they can do one complete puzzle. Right? They can do one complete puzzle working together. Well, this is another rational equation. This is another rational equation. Any questions so far? These applications can be a little more difficult because you're not going to be given the equation. You have to set it up. Right? You have to set it up. Well, is the LCD 8 times H? Sure looks like it. So if we multiply everything by 8H, this is going to cancel. This is going to cancel. And that's all that's going to cancel. All right, so our goal was to not have any fractions anymore. And I believe we got there. Right, I believe we got there. So what are we left with? 4.5H, 4.5 times 8, which is 36, and 8H. Now, not trying to be mean, but if we can't solve this, what's left now? We're probably in the wrong math class. That's what you called probably a two-step equation back in Algebra 1, right? What would you want to do to get H by itself? You'd have to get the H's together, wouldn't you? Right, so if you subtract 4.5H from both sides, you get 36 equals 3.5H. And to get H by itself, we would have to divide by 3.5. Well, that means H is 10.3, which means if Renzo was working on the 500-piece puzzle himself, it would take him 10.3 hours. All right, it would take him 10.3 hours. Okay. All right, so the idea there is we're looking at applications that we're going to have to use the idea of solving a rational equation. Okay. those take it to another level. Right, those definitely take it to another level. Okay? Questions? All right. Now, last idea in this, in this section 5 here, and we can go back to other things if you'd like to. Like I said, if you're not sure how to do something, ask, because your question will probably help everybody. I'm assuming you watched the videos and you kind of picked up on how to solve these equations for today. If you didn't, I need to know that, okay? All right. Now, rational inequalities add another layer to solving rational equations, okay? A rational inequality is an inequality that contains one or more rational expressions. One way to solve those is by using graphs and tables, okay? All right. I'm not going to rely on graphs and tables. I think it gets to be too confusing. I truly do. Okay. I think the best way is to use the LCD method. We're going to solve these just like we solved algebraically, with one exception. When we solve these rational inequalities, there's going to be two cases. Okay. One of them is if the LCD is a positive number. The other is if the LCD is a negative number. Now, the reason we have two cases here is if I had an inequality like this, okay, well, let's do another one first here. If I had an inequality like this, what would I do to solve this one in red? Yeah, you're going to do just like you do in algebra. You're going to divide by 4. And if we divide by 4, x is greater than or equal to 5. Now, what are we going to do over here to solve? We're going to divide by -3. Now, what happens, and you learned this back in Algebra 1, what happens when you multiply both sides of an inequality by a negative number? Okay. Now, that's why we got to switch the symbol, right? That's why we're going to have two cases when we're solving the rational inequalities. Some values of the variable could make it positive, some could make it negative. So we're going to have to do basically two cases. All right, we're going to have to go with two cases here. All right, and that'll make more sense, but this is why, because we have to change the sense of the inequality if we multiply by a negative. All right, so half the work will be just what we've been doing. The other half we'll have to put a little twist on. All right, let's solve this one algebraically. 6 over x minus 2 is greater than or equal to -4. Well, what's the LCD here? What would we multiply both sides by to get rid of the denominators? X minus 2. Now, case 1, we're going to say x minus 2 is positive. We multiply both sides by x minus 2. We end up with that. We cross off the x minus 2. Notice the inequality symbol stayed the same. Multiplied by a positive. We got 6 is greater than or equal to -4x plus 8. Solve that. Here, can you see that it switched? And why did it switch there? What did we do to solve that? Divided by -4. Okay, divided by -4. All right, that's part of our solution right there. X has to be greater than or equal to 1/2. All right, pretty straightforward solving inequalities there. Okay, now the key component there is that we said the LCD is positive, so we didn't change our symbol right away. Okay, now the second case is going to be, what if the LCD is negative? All right. All right. All right. Now, what if the LCD is negative? Well, that means if I multiply both sides by x minus 2, can you see what happened here? If the LCD is a negative number, if I multiply both sides of an inequality by a negative, do I have to flip that symbol? Okay. And now we can proceed right? The key part was making sure we made that change there. We get there, and then we solve that, and we get x is less than or equal to 1/2. Okay. All right, so there's two cases, possibly going to be two cases when we're dealing with solving these inequalities. Okay, and it's because of the rules for solving inequalities. You multiply both sides of an inequality by a positive, everything stays the same. If you multiply both sides of an inequality by a negative, we have to change the sense there. Okay. Now, then we're going to have to put those together. And I think our solution, let me get rid of this writing here. I think we put those two together. This is the solution we end up with. X has to be bigger than 2, or X has to be less than or equal to 1/2. All right, the solution set is the union, or we got to put those two sets together. Okay, we have to put those two sets together. All right. Questions on that? Now, I'm going to show you how to do it graphically, and if you really want to do it graphically, you can. All right. The algebra can get pretty deep here, right? That problem, did it get pretty deep? It's a lot of work. Okay, it can be done algebraically, but if you want to use graphs and tables, I'm going to say go right ahead. All right, for inequalities. So if we're going to do that, I need to go to Desmos. So give me a second here. All right, so we're going to go to that graphing calculator. Now, I believe, and Desmos is different, but than I'm used to, but I believe I can just type this in here. 6 divided by x minus 2. When is that greater than or equal to -4? All right, now, let's see what we end up with. Okay, I'm trying to. It's not changing for me, is it? Anyway, let me go home here. Okay, that's what our solution set looks like. Now, basically, how do we interpret that? Does anybody know? I do, but I'm asking you if you do. All right. Basically, what that means is on a number line, this would be our solution set. Oops, let me go back here. Give me a second here. Okay. Now, it just so happens this is when x is greater than 2. Wasn't that part of our solution set earlier? It was, wasn't it? What was the other piece? X is less than or equal to 1/2. Well, I'm willing to bet that this point right here is 1/2. All right. All right. Our solution was, to make sure here, x is less than or equal to 1/2, or x is greater than 2. So what do you think is easier, the graph or the algebra? I think the graph is easier. Okay. Yes.
When you use the algebra, the x minus 2 is the denominator stays the same both times. You just say it's a negative the second time.
Yes. Basically, we said the first one, if the LCD is positive, you would say x minus 2 is greater than 0 because that's a positive number. Okay. If you said the LCD was a negative, you'd say x minus 2 is less than 0 because that makes it a negative number, right? All right. So any other questions? So yeah, I think I don't want you to get too heavy duty into these inequalities. I'm going to tell you right now, if we see an equation on a quiz, I want to see it solved algebraically. Now, can we check our equations on Desmos? We've done that throughout the whole year, haven't we? Okay. Inequalities, some of that algebra can get a little hairy, so I think we're gonna spend more time solving those algebraically, or excuse me, graphically, sorry. Okay, so here's what I want to do now. I want you to try one graphically. See if you can solve that graphically. All right, take a few minutes, solve that graphically. Which means you're going to have to come up with those statements like we just had. X is less than or equal to 1/2, or X is greater than 2. All right, take a few minutes and do that. So you're looking for where things are shaded, right? And maybe putting in what it would look like on a number line might help. I don't know. So once again, we still have to be able to interpret what we see, right? Desmos isn't going to tell you what the solution is. You're still going to have to interpret what you see. What does that mean? What is that graph really representing? Okay. All right, so I'm going to share my screen here. And you should be able to type it in just as it's written. And I wrote it up here so I wouldn't forget. 9 divided by x plus 3 is less than 6. All right. Now, is that what it looks like? All right. Now, is that what yours looks like? Now, let's talk about some things. Why is there a dotted line right here? Well, that means x can't be that value, right? So let's look at things. This is what this would look like if we did this on a number line, I believe. Very similar to the last one. Agreed? Now, what is this going to be as an inequality? X is greater than what? What does that number appear to be? Negative 1.5 or negative 3 over 2. Everybody agree with that? Okay. Now, what is this one? This one appears to be X is what? Less than? Is it negative 3? It is negative, right? It is negative. Now, seems to work for me. That's what we're interpreting. Once again, you still have to think. We still have to say, what is that graph telling me? All right. And if you need to zoom in or zoom out to find those values, I think that's something you can do. Question?
So there's a dotted line on x is less than, or x is greater than negative 1.5. Or is it negative positive?
If it was a solid line, I think it could be equal to. But there isn't a solid line here, is there? Because why can't x be negative? X can't be negative 3, can it?
No.
Because we divide by 0. Okay.
So
But if there was a solid line, I think you'd have the equality issue. But we don't have equality here, so that's not showing up there.
why isn't that a dotted line?
This is a dotted line. This is just a border because we can't let x be negative 3. Otherwise, it'd be dividing by 0. Okay.
Okay.
Because of the way the fraction's set up, that's a value that causes us to be undefined. Okay. Now let's take a minute to check Let's check things. Give me a number that's less than -3. Right? -5. Is 9 over -5 plus 3 less than 6? Well, that's going to be what? 9 over -2, that's -4.5. Is that less than 6? Yeah, it is. Okay. Let's try another number. Give me a number that's bigger than 3 over 2. 0. Okay. 9 over 0 plus 3 is 3. Is 3 less than 6? Yes. So we can kind of check our answers too. Now, Jackson picked 0. I like that because the 0 easy to check. It is. Okay. -5 was pretty easy to check also. Okay. So we still have to interpret what the graph is telling us. All right. We still have to interpret what the graph is telling us. Okay. So we're not going to spend a lot of time solving these algebraic. It is confusing. Okay. I'm not gonna dwell on that when we have the technology to take care of a lot of that. But once again, a reminder: do you still have to think? You still have to think and interpret what you're seeing. Right? We're looking for where we're shaded. Right? And realistically, what I drew in here in blue, that's really what that would mean if we remember when you solve things on a number line, you had open circles and arrows going in different directions, right? Yeah, that's how we're looking. Okay. All right. Any questions? And I'm just going to scoot ahead, and you're going to see that it's the same solution set we ended up with. X is greater than -1.5, or X is less than -3. That's exact same solutions that we came up with without all the algebra. Okay, without all the algebra. Okay. So use Desmos to help. Right? Use it a lot. I've been telling you that a whole year. Don't rely on. Use it to check things. So here we're going to use it solely for that purpose. All right, here are some questions to work on for Thursday. Thursday, we're going to get a little bit into section 6, which deals with radical expressions and rational exponents. And then we will have a worksheet, I believe, on Friday. Okay? All right. You have a little bit of time to get started.